Hello everyone, I'm Xinjie Lan. I'm glad to share my recent work, a probabilistic representation of deep neural networks, bridging mutual information and generalization. And the co-author is Chris Sparner. He is my advisor. Deep neural networks are well known as over-parameterized models without explicit recognition. However, we surprisingly found neural network has very good generalization behavior simply by its SGD method. This phenomenon is beyond the interpretable scope of conventional statistical linear theory, such as VC dimension, Rodemacher complexity, and uniform convergency. A natural question is that how can we accurately measure the generalization behavior deep learning? Recently, mutual information becomes a popular approach to bound the generalization error, specifically the mutual information between a hypothesis and the training samples bounds the generalization error. That means if a hypothesis learns less information from training samples, it would generalize better. However, there is a problem. The accurate mutual information estimation is intractable due to the complicated architecture of deep neural network. As a result, most works have to relax the mutual information to some tractable variables, such as the Lipschitz constant of the empirical risk, the second moment of gradients, and the incoherence of gradient. A relaxation inevitably loosens the mutual information bond and also weakens the information's relative explanation. So in this work, we try to derive an accurate mutual bond. To that end, we propose two methods includes two steps. First, we study the Markov chain and to characterize the information flow in deep network. Second, we define the probability space for a single hidden layer, so we can accurately estimate the mutual information between a single hidden layer and training samples. Now let's first go through the information flow in deep neural network. In general, the information on training samples can be decomposed into three parts: the yellow one, the pink one, and the red one. Since the conditional entropy distribution PYS given XS is commonly defined as the one-hot format. That means if the Y equals the target label YJ, the probability will 1, otherwise the probability will be 0. So the conditional entropy HYS given X is 0. And the red part is gone. So we can decompose information of training samples into two parts. The first part is all the information irrelevant to target labels, and the second part is all the information of target labels. A learning algorithm learns the information from both parts, so the information between S and W can be simplified as these two parts, which corresponding to the blue area and the red area in the Venn diagram. Now let's look at the information flow in deep neural network. We prove that the XS bar satisfies the Markov chain start from X bar S to the first hidden layer until to the output layer. Therefore, we can simplify the mutual information between X bar S and W as the mutual information between X bar S and T1. In addition, we know the output layer has all the information of target labels in a well-trained deep neural network, so the mutual information between YS and W can be simplified as the mutual information between YS and Y hat. Finally, we can say the mutual information between S and W can be simplified as a summation of these two parts. In this slide, we define the probability space for fully connect clear. Based on the definition of cross correlation for the fully connect clear, we know the weight of a neuron defines a global feature for the input, and the activation measures the cross correlation between the global feature and the input. So the random process, a hidden layer, can be defined as recognizing the feature with the largest cross correlation to the input Z. Therefore, we define the probability space as follows. The sample space omega t consists of n possible features, and each feature is defined by the weight of each neuron. And the event space is sigma algebra. We define the probability measure as Gibbs distribution to quantify the probability of each feature being recognized as a feature with the largest cross correlation to the input Z. So we have the conditional distribution Pt given Z. We also define the random variable T here, so we can derive the marginal distribution Pt, and we can derive the condition, the transformation between xs and t. In addition, we can also derive the conditional distribution Pt given ys, so we can derive the transformation between ys and t. Finally, we can derive the transformation between x bar s and t. The last part is our experiment. We generate a synthetic dataset through evenly rotated a deterministic image in 4 different orientations. So the synthetic dataset has 2 bits information. The binary labels has 1 bit information. We choose the incoherence of a gradient as a relaxation. It will relax the mutual information bond and the conditional mutual information bond. We define 6 networks here. MP1 to MP3 are trained on the synthetic dataset. MP4 to MP6 are trained on the fashion mix dataset. First, in this slide, we validate the mutual information estimator. From the top right finger, we can say the information of x bar s flows in the forward direction. So it validates the marker chain we proposed in the first slice. In addition, on the bottom left finger shows that as the empirical risk quickly converges to 0, the outer layer quickly learns all the information of tag labels. So the information between ys and y hat can be used to estimate the information between ys and w. In addition, the bottom right finger shows that the information s and w quickly converge to the entropy of training samples. So this finger demonstrates the mutual information estimator. Finally, we compare our proposed model and the 2 relaxation method. In the first row, we can say that our proposed information bond derives a more accurate estimation for the generalization error. In the MAP 1, we can say our bond is close to 2, which is much lower than the relaxed CMI bond is over 40, and the relaxed MI bond is over 18. So our mutual information bond is more accurate than the relaxation method. We also see the similar result for other MAPs on the fashion mix dataset. All right, this is my presentation. Thank you.